Hello, thank you so much and welcome to this session of ionic equilibrium. In this video, we are going to be covering pH of solutions of weak bases. And we are starting with ammonia, which is a typical example of a weak base and reacts with water to produce hydroxyl ions and ammonium ions as seen in this equation that we have here. So the ammonia is acting as a base by accepting a proton from water molecule, which means the water is now acting as the acid. But because most of this ammonia remains unionized in water, it makes a weak base. So the equilibrium lies to the left of the equation because ammonia is a weak base and only partially ionized. The next thing you want to do here is to obtain the expression for Kb by applying the law of mass action. If you apply law of mass action to this equation, we shall be obtaining an expression of Kb. We say Kb is given by molar concentration of ammonium ions times molar concentration of the hydroxyl ions divided by the molar concentration of ammonia. Now you don't want to include the molar concentration of water because it is just taken to be a solvent and it is in the excess, so there is no serious change in the concentration of water or in the amount of water. Then the next thing we want to do here is to obtain the simplified expression for Kb, and this is done by taking some assumptions. And assumption 1 here is we assume that the molar concentration of ammonium ion is equivalent to the molar concentration of the hydroxyl ion. The ratio is 1:1. If there is no another reacting species added that can take aid of the ions, the concentrations of the two should be the same. Then the next assumption you want to take is about the molar concentration of ammonia, which is approximately remaining constant. Reason being, the ammonia is a weak base and it is only partially dissociated, which implies most of it is going to remain in solution as unionized ammonia. So we say molar concentration of ammonia is approximately constant. So if the initial concentration of ammonia is C, it means the molar concentration of ammonia is going to be equivalent to C moles per decimeter cubed. So if we substitute for these assumptions in our Kb expression, we come up with Kb being equivalent to, where there is molar concentration of ammonium ions, now we substitute with molar concentration of hydroxyl ions. So this will give us molar concentration of hydroxyl ion squared divided by C, where C is the original amount of ammonia that was present. Now, in this case, we're looking for expression for pH, which means we have to simplify this expression further until we get something that helps us to calculate the pH of a solution of a weak base. So you want now to make the concentration of hydroxyl ions the subject. You obtain molar concentration of hydroxyl ion is equivalent to the square root of Kb times C. So this is the molar concentration of the hydroxyl ion as expressed from the equation. Sometime back, we found out that if we have molar concentration of hydroxyl ion multiplied by the molar concentration of hydrogen ion, this would give us the ionic product of water. And we want to do away with the molar concentration of hydroxyl ions, which means we can make it the subject here and then we substitute in that expression. So molar concentration of hydroxyl ion is going to be expressed as Kw, ionic product of water, divided by molar concentration of the hydrogen ions. So if we baptize this as equation 2 and we name this one as equation 1, we can simply say equation 1 is equivalent to equation 2. That's one thing we can see. So what we have next is ionic product of water divided by molar concentration of the hydrogen ions is equivalent to the root of Kb times C. So we can simplify this and get the expression for molar concentration of hydrogen ions. So here you cross multiply, then again you divide by the square root of Kb times C. You come up with molar concentration of hydrogen ions being equivalent to ionic product of water divided by the square root of Kb times C. Now that we have expression for molar concentration of hydrogen ions, what we want to do next is to substitute this in the pH expression. pH is given by negative log to base 10 molar concentration of hydrogen ions. And from here, what we have already, we have the molar concentration of hydrogen ion is being given by the Kw divided by the square root of Kb times C. So what you want to do next is to substitute that in the pH expression. So our pH becomes negative log to base 10 of Kw, ionic product of water, divided by the square root of Kb times C. So this expression should give you the pH of a solution of a weak base once given the Kw, Kb, and the initial concentration. Now the Kb that we have in our expression is what we call the base dissociation constant. The base dissociation constant. C is the original molar concentration of the base. Kw is the ionic product of water. So this is one of the equations that we can use to calculate the pH of solutions of weak bases. Then, if you hadn't done this, you could simply move from the very first equation, equation 1 here, and then you come up with an expression for the pOH, then which you can use to obtain pH. So from equation 1, we could simply say pOH is given by negative logarithm to base 10 molar concentration of the hydroxyl ions. And the molar concentration of hydroxyl ion has been expressed as the square root of Kb times C. So what you want to do next is to substitute for molar concentration of hydroxyl ion, so that our pOH is given by negative log the square root of Kb times C. Then after obtaining this, you will now substitute in an expression pH plus pOH is equivalent to 14. And given Kb value and the initial concentration of the base, you will be in position to obtain the value of pOH. And after obtaining pOH, you simply obtain pH by getting 14 minus that value of pOH. So these two equations should be in position to help you calculate the pH of a solution of any weak base. So let's look at one example under this calculation. We have a question here. Say we're supposed to calculate the pH of a 0.001 molar ammonia solution. If you are given the base dissociation constant of ammonia as 1.8 exponent negative 5 moles per decimeter cubed, and the ionic product of water as 1.0 exponent negative 14 moles squared decimeter per negative 6. Now the first thing you want to do here is to obtain the equation which I already have on my left hand side here. So all I need to do is to just obtain the Kb expression, and we have just completed that. So using the expression for the hydroxyl ions concentration, we are going to find the molar concentration of the hydroxyl ions that is produced by 0.001 molar ammonia solution. So we can say here that our initial concentration, which is C, is 0.001 molar. So we have that information. And then we obtained previously that molar concentration of hydroxyl ion is expressed by the square root of Kb times C. So now that we have the value of Kb and we have the value of C, we simply substitute in this equation and we obtain the molar concentration of hydroxyl ions. So this will give us molar concentration of hydroxyl ion being the square root of 1.8 exponent negative 5 times 0.001. So molar concentration of hydroxyl ion is expressed as, you can put that in the calculator, 1.8 exponent negative 5 times 0.001, and then you get the root of your answer. This gives us 1.3416, which is 2 exponent negative 4 moles per decimeter cubed. Now that we have this and we have been given the Kw, we can now write an expression for the ionic product of water. That is, Kw is given by molar concentration of hydroxyl ions multiplied by molar concentration of hydrogen ions. Kw is a known value. Molar concentration of hydroxyl ion is also known, so we're only going to look for the molar concentration of hydrogen ions. Molar concentration of hydrogen ions, therefore, is Kw over molar concentration of the hydroxyl ions. We substitute for this. Kw is 1.0 exponent negative 14. This divided by 1.342 exponent negative 4. So we're going to have 1 exponent negative 14 divided by our answer, which is 1.342. This gives us a value of molar concentration of hydrogen ion being equivalent to 7.453559, which is, we can make it to 4 exponent negative 11 moles decimeter cubed, moles per decimeter cubed. Then from there, we can simply obtain the expression pH is given by negative log to base 10 molar concentration of hydrogen ion. And our pH can be obtained by substituting for the value of molar concentration of hydrogen ion 454 exponent negative 11. So what we want to do is to get negative logarithm of our answer, and this would give us the pH of 10.13. It is 10.128, so we can round it off to 10.3. So this is our pH of a solution of 0.001 molar ammonia solution, and that is the simplified calculation. So if you don't want to use all this approach, the simple way you could do this is, after obtaining the molar concentration of the hydroxyl ion from this part, you would simply come here and say pOH is given by negative logarithm to base 10 molar concentration of hydroxide ion or hydroxyl ion. Then we obtained our pOH. pOH is given by negative log of 1.342 exponent negative 4. So we say negative log 1.342 exponent negative 4. We obtain the pOH as 3.87. That is our pOH. Then now we have that pOH plus pH is equivalent to 14. That is from our pH scale that we calculated at 25 degrees Celsius. So pH can be obtained from 14 minus pOH. We substitute for the value of pOH. This will be 14 plus 3.87. So we get 14.387. Their pH for that solution is 10.13, which is the same as what we had got before. So that is the way you can calculate the pH of a solution of a weak base when given the base dissociation constant, that is Kb, and the ionic product of water, which is Kw, and the initial concentration of that base.